Hello, it's David. Something slightly different today. While I've been working on the Falkland PSU, I've noticed that sort of amongst the detritus at the back of my workbench here, along with the cheap Chinese component tester, a partially disassembled DFB1 revision 3, and a whole host of little abandoned circuit boards, is one of these. This is one of my Smalliermouse 2 clone boards, the Smalliermouse. This is based on a design by Simon Innes, which was originally for the BBC Micro, but it was basically a quadrature mouse emulator for USB mice, modern USB mice, using an Atmel 1287, I think, not 1890 1287 chip, because that has a USB hosting capability. And this has just been laying around here, but I actually think I've got enough parts to put this together. I can reclaim a 9-pin DE there. I've got a spare 1287 because I thought that was bad. It turns out it's not. And there's not much more than it needs. There's the DB or DE9 connector, female. There's the USB-A, socket there. That one's a bit rusty. I might have another one. There's a 16 megahertz crystal that I think I've got somewhere, and then otherwise it's mostly passives and the occasional jumper. So why not? Let's build this up. But before that, let me explain why I've refactored this board, and the firmware, by the way, for the Ataris. Okay, so firstly, apologies for the lower quality screen here because of the wider angle that I require. This is the opposite lens on my phone. But here I have my 4MB STE, otherwise stock, connected here in low resolution. This is it has a modern cheap laser mouse on it, and this is connected up with a TOM2 USB to Quadrature interface. This supports the ST. This is an STE, by the way. It's just got my Falkland keyboard in it because while I work on the Falkland, I don't want to ruin the keyboard. Now the problem I have with this, I mean, you can see that it works if you move incredibly small amounts. This is because of the high resolution of the modern mice. If you work at incredibly small amounts, then yeah, you can kind of get away with it. The accuracy is not. It's difficult because you have to move such a small amount, and if you try and move too quick, well, not much happens. You get that incidentally with the original bull mice as well. You could quite easily take one of the higher DPI bull mice and whisk it quickly across the desk, and the mouse would just shudder. If you spin the little roller inside, you'll see that effect as well. And that's because the Atari range, for some reason, has a very low limit on the number of quadrature inputs per second. And that's actually one of the reasons why we want some custom firmware. And I think all the TOM2 must do here when you put it into ST mode is to simply truncate it. Because the biggest problem I have with this is when you get to a certain acceleration, a certain speed across the screen, it never goes faster. It's like driving it with a joystick. It gets up to speed, and then there's a maximum speed, and you will not go past that speed. It's maybe more obvious in high res, but I'm not sure whether that will come out on camera. So here we are on high res, and you see we've got more screen to cover, and now it's a lot harder for me to get the pointer. That is full speed. That's how hard it is to get the pointer across the screen. Now that is not And that is just like doing this with a control pad. That is not how a mouse should work. So my aim was to improve on that. So what I did is I looked at the best quadrature mouse simulator, open source one on the market that I could find, and that was Simon Inn's Smalliermouse, and that's got a broad range of compatibilities. So it comes in quite a chunky box, and you have independent power supply and lots of different header configurations to go to different machines. So by targeting specifically the ST, can cut down on a lot of the complexity and target the firmware specifically for it. So we'll get rid of our Tom2, and here is a Smalliermouse, built up one. It's designed in this strange shape to fit underneath the keyboard, and just allow the mouse wire to connect in as if it were a normal Atari mouse. However, I'm using my extension here just for convenience. So this has already been flashed and set up, and it should be configured well for high DPI USB mouse. Let's give it a try. I should say that these really are intended for wireless mice, because the amount of strain to put on the ST's mouse port to power both the actual chip and the mouse is actually beyond spec. So it's really targeted at using wireless mice with little dongles, which are a lot lower power. But anyway, here we go. We can see it works. This has features scaling factors. This features maximum quadrature rate, and it has a certain degree of tuning to allow for things like catching up. There's a certain number of milliseconds that it is allowed to catch up after the mouse stops, and that can be configured in firmware depending on your personal tastes. But look at this. You can still see there's that maximum speed, but that is a lot better. I can whiz across the screen considerably faster, and the accuracy is improved. The reason is I have to move further to go a set distance. When it's at slow speed, it accelerates up like you normally expect. And here is the advantage over the stock Smalliermouse firmware. When you are at low speeds, it counts missed pulses to allow smooth motion even at very slow speeds, and that one is actually conversely more easily seen in a low resolution mode if you're trying to play Populous or Civilization or something that requires you to be very accurate with your positioning. Here we go. You can see you can position relatively well to within 1 pixel right, 1 pixel up and to the right, 1 pixel 2 down. Okay, that's my hand more than anything else, but you can see the level of accuracy that is able to be achieved here, and that is the big advantage of the Smalliermouse over ubiquitous items like the Tom2, which, let's be honest, they're really intended for the Amiga. The ST is a complete afterthought. You do get some PS2 adapters, and those obviously work a lot better. The PS2 protocol is a lot closer to the old quadrature protocol. It's easier to translate. You get better results. But we're only delaying the inevitable with PS2. USB has completely replaced PS2 in the PC market. How long is it going to be that you can source PS2 mice? Hence the Smalliermouse. So let's have a go at building one up. Okay, so first things first, we need to give the board a good clean. It's been laying around here in all the filth on my desk, so let's give it a bit of a scrub. And then I think we probably should be starting with the main chip. It's the most low profile, it's almost by itself. there's a capacitor on this side, and then the DE9 will go on last. So let's get that cleaned up, and we'll start off with our SMD work. These boards, by the way, were ordered from OSH, OSH, Open Source Hardware Park. It's a US company, nowhere near as cheap as JLC PCB, but for tiny boards, they're not bad value. They charge per square inch because they're Americans, but for something tiny like this, I think three boards supplied, they're a reasonable value. Shipping's free, well, it does take a little while from the US, and as you can see, all of the pads are gold plated as opposed to the more usual standard tin affair. Come on, let's have a go out. Now I believe this chip is working. Obviously we'll find out if we build this up, and it won't flash the firmware. But I simply had suspicions about the chip, and so replaced it for the new one on one of my other working boards, which was sent to Exos, by the way, for his evaluation. Turned out that was just a bad resistor connection on the USB data line. So got myself a bonus chip. Now this all designed in KiCad, by the way. This is completely open source. This is someone else has designed. I've refactored. It's all available on my GitHub. Pin 1 over in that corner there with the longer line. That's how KiCad does. Pin 1 for QFPs. So one of our pins is a little bit bent there. That looks better. This is massive overkill, this chip, for a project like this. However, you can tell by the number of non-connected pins on here. However, it's the smallest Atmel chip that does USB host mode, which is what you need if you're going to emulate a PC for the USB mouse connecting. Now, when I'm doing SMD work, I don't have a microscope. I'm not good enough to solder through the viewfinder on the phone, so I use one of these head-mounted loops like this with interchangeable lenses, and I can go from, I think that's probably 3 times, and that's another 2 times on top, so just lets me vary my magnification levels. I should try not to poke into the way of the camera too much. You do need to get very close with these, so that might make for poor viewing. Perhaps I'll bring the camera in for this. Okay, because I have to get quite close with the head-mounted loop, I'm having to bring you in a lot closer here. So apologies if I stick my face in the way. Okay, so first things first, on the Atmel chip, the dot indicates the pin 1 corner, and the pin 1 corner, as I said, is marked over there. So we're looking at this orientation. So the trick is to try and get, by the way, these ones are not too bad at all to solder. The pitch is really quite forgiving, and modern day solder mask, and sufficient flux is really very simple. The hardest bit is just getting the alignment correct first time, and obviously the trick is covering everything up there. Sorry. Obviously the trick is that you make sure one's aligned, you make sure its perpendicular neighbour is aligned, just nudging fractions of a millimetre at a time. You go back and check the top one, then you move to the opposite side and down to the bottom. That to me looks absolutely fine. So you anchor one corner, plenty of flux, and what we want to do is to get a good decent blob of solder on the end of your tip and just go overboard. I actually moved that a little bit, but such is the forgiving nature of these this pin pitch, that still is fine. I think the alignment there is okay. So then you move to the opposite corner and repeat the process. Good blob of solder. Anchor it. And there's absolutely no problem if it's a huge blob like that. Once it's anchored, and therefore immobile, we'll just inspect again to make sure the alignment is still good. Now you may be able to make out that on this side it's not entirely perfect. They're not on the center of the pads, but there's no chance of shorting and they will definitely make good connection. And similar on the other side. They're not quite in the center, but the alignment is good enough. And on the top and the bottom, they're absolutely fine. So we can continue. So we move on to one of the sides that we have not anchored. And the key to any of this is a good amount of flux. Yes, we'll have to clean it off afterwards, but it will make our life a lot easier right now. Now, we don't need anywhere near as big a blob this time. That's probably actually too much. But let's give it a try. Turn my fuming extractor back on again. This is where the K-tip is the one I prefer for SMB soldering. And this is where this comes in handy because it's very good for dragging. That is not behaving as I hoped. It's not leaving any solder on the pads. Maybe it needed more cleaning than I initially thought. Let's try the other side briefly. Give up. iron and jolly good clean. That is more to my expectation. Bit more solder. And then it stops again. See how nicely that flows on the first 2/3. That's what we're expecting to see. And then it just stops. I think the board is not sufficiently clean. Bad example of how to do it. How much more can I clean this? It's definitely touching the pads. It's not that we're just... No, the pads should take the solder anyway, even if they're not touching. There we go. Damn it. I did an insufficiently good job first time around. Right, let's get some more flux on that. So I've cleaned all that off. And then we should see that flow a lot better. So I've cleaned my tip. I'm just redistributing the solder that's already there now. You see, I'm dragging along here. I'm moving the excess all the way down to the last pin or two. And obviously there's a massive bridge there at the moment. Smaller, don't know if you can see that, smaller bridges can be removed by just cleaning the iron and dabbing in and out. Yeah, like that. Oops, sorry, that's my loop. That looks pretty reasonable. Time for the third side. With the exception of those final two pins, that is how it's meant to work. That looks almost perfect first go. obviously we clean this up and come back to inspect. I believe that's fine. So let's move on to the other components on this side. So we've got basically a single passive capacitor 8. Just going to do a little bit of cleaning up because this solder flux paste that I use, I don't remember the brand, they come in syringes. It's very, very messy. It's very, very good, but it's very, very messy. I've got this MG Chemicals No Clean version. When this one runs out, be interesting to see how that behaves. I have a small vat of propan-2-ol that I tend to soak things in overnight if I really want to get them clean. Don't have a ultrasonic cleaner. That's for the pros. Right. So C8, turning to our schematic. C8 is 100 nanofarad header decoupler. I've got a feeling that should perhaps be a higher capacitance, given that that's connected to the main board, but I'm going to go with my original spec for now. And how I do have my passes is I get one of these sample books, or I have one of these sample books, which contains a whole load of, these are all 0805 components, contain a load of resistors and capacitors, and I just stuff a few extra things in that I acquire. So we're looking for the 100 nanofarad, that's by far the most common. So you see we've got 4 rows of that, and I'm running out on my first row. I'm about halfway through that. It's been replenished once already. And we will end up using a few of these. There are 1, 2, 3, 4, 5 100 nanofarad caps required on this board, so we should probably actually clean both sides and go around and do them in one go. Now for individual 0805 components, you could just as easily use one of the fine needle tips for soldering rather than the K-tip that I tend to employ. And these very fine needle tips are good for touching up they're very fine. Very good for touching up SMD mistakes, but my tip is hot and the board is not particularly dense, so I think we'll have no problem with the K-tip in this case. So my trick is to peel this back one at a time to expose a single one, drop it onto the desk, and then 2 at a time. So let's get our smear of flux on each pad. And again, let's try and do this without blocking the shot. So, merest hint of solder on the iron. Situate the capacitor on the pad, touch both pad and and component. I think I'm having the same problem here actually. This maybe is a layer of dirt. There we go. How to actually get a better connection on the pad itself. I maybe do need to switch to the needle nose. Now you've seen what I've done there is just hold that capacitor down after having done it first, and then just retouch, and now it will be flat on the board, and I should be able to do the other side. Yeah, I'm struggling actually to get heat into the pads. The iron's hot now, so I don't intend to change this, but because I think that this board has been sat around here and exposed to oxidation, in this case, the needle point might have been better for the passives. Anyway, that's C8 done. So the other 100 nanofarads are all of the 8090 ones. So that's C5, C6 and C7. Yeah, none of them pretty, but they're all intact. Okay, I think I'm going to let the iron cool down and switch to the needle tip. Okay, so I've switched to the needle tip on the soldering iron. We'll move on to that's now heated up, and we'll move on to the other passive. So next on my list is the 22 picofarad capacitors that go either side of the crystal. So that's C1 and C2. I think we'll have to resort to a slightly different technique here of actually tinning the pad. So you put a great big blob of solder onto the pad like that. You try and hold your component from one end, preferably flat. You melt it, and then you introduce the component. Hold it down, remelt. This is not normally my this is not normally my favourite technique, but it seems to work better with the needle nose. There we go. So that's all of the passives in place. Next up, it'll be the crystal Y1 here, and this is a 16 megahertz. SMD crystal, 5mm by 3.2. And here it's slightly different because the pads are underneath the crystal. They do extend to the end, but they flow underneath. So here we will pre-tin. melt the solder. Oops. Don't get it stuck on the flux. Melt the solder, introduce the component, hold it flat, remelt. And on the other side we should just be able to flood the pad, let it work its way under. That's nice and flush to the board. Just take a moment to inspect the main chip whilst I'm still working on the SMD components. Don't see any problems other than it being dirty. So I think that's time for a cleanup, and then we'll move on to the through hole and the connectors. Right, so I've changed my tip to the screwdriver chisel tip for doing the remaining components, which are mostly through hole. But whilst that's going on, whilst that's warming up, just show you a way to handle some of these drunk looking chips if that's getting on your nerves. Personally, it doesn't bother me, but I don't have the OCD that some guys do. So plenty of flux. Time to bring in the heat gun. So I'm setting that for 330 degrees. I'm turning it up to about halfway because I don't want to blow the components off the board. And I'm just going to heat them up. Just warming the board in general at first, but then I'm going to focus on those two resistors in the middle, the two 20 ohm USB data channel resistors. There we go. Did you see that? They've snapped to alignment. Try this capacitor in the corner here. When it starts to flow, you'll see the surface tension of the solder just pulls it in onto the pad. Oh, that one there, C5, just aligned. The others actually, I think, are pretty good. Maybe this one in the corner here. R3. There we go. You can see that those two can I get the focus? Those two 20 ohm resistors are now nice and straight. Now for the USB connector, we've got this USB-A socket. This is a combination through hole and surface mount. So the four connectors are surface mount, and it's got a couple of through hole anchors. and see that those will protrude through the board, and the 4 pins will align on the pads. So I'll just push this into place there. And the first thing we'll do is we'll solder the 2 outer ones to make sure that they're flush. So holding it down, heat pad and pin. And that should now be physically bonded. So I'm going to flip it over and solder the anchors. Right, sorry about that, my battery ran out. So I'm now just going to solder the anchor points. Feed a lot of solder in there. And now on this side we'll finish off 2 in the middle and reflow the end bonds. The 2 in the middle being the data lines. Now the DE9 connector is actually a solder, a wire solder terminal designed to fit in the little housings, little plastic housings that you see. Goes into the back of computers. These ones, so designed for wires to go into the end and to make cables. However, because of a good bit of design, the gap between these is pretty much exactly 1.6 millimeters, i.e. the thickness of a PCB. So with the 5 connectors on the top and the 4 on the bottom in the appropriate place, these can be jammed onto the end of the board and soldered down. Sometimes needs a little persuasion to get going. There we go. that looks pretty good to me. Then the only two remaining things on here that need to be permanently soldered are the jumpers. Now, to be honest, they don't need to be permanently soldered. These are mostly optional, but I'm going to add them anyway. The first jumper controls the DPI division, enable on the firmware, and the second one is the programming mode, which we will need at least once, and there's no harm having it multiple times or being able to use it multiple times, because this is open source firmware and you may wish to change the settings. Right, so this is now time for a jolly good cleanup, and there's one more thing we have to do, which is to program it. So first of all, let's get this soaking in some IPA, and we'll come back and we'll look at the firmware. So just for the purposes of firmware programming, I've soldered a short bit of wire onto the reset test pad. And what we do when we're going to program this is to take our jumper, and we only need a single jumper for this because we shan't use both of these at the same time. We'll take our jumper and we'll put it onto J5, which is the programming mode header. We then need a USB-A to USB-A cable. This one's seen better days. These are relatively cheap on Amazon or eBay. This one's probably too cheap looking at it, but it still works. So the USB to USB-A, USB-A to USB-A plugs into your Windows PC, and it does have to be a Windows PC because Atmel Studio is based on Microsoft Visual Studio. So virtual machine time. We plug into the Windows machine and we connect it here. Nothing happens on the device manager. However, if we now ground our reset point, and the easiest place to ground to is this enormous great USB socket here. So we just touch this here and release. And there we go. On the device manager, we now see the Atmel chip detected. With Smalliermouse 2 now connected and in programming mode, we launch Atmel Studio and we load our Smalliermouse 2 solution. Now the main thing to be interested in here is at the top of the main.c. This sets a few limits. So the Q rate limit is the quadrature output speed, the maximum quadrature output speed. Now this is very low on Ataris. A lot of other computers can deal with rates of 1,000 or more. You can see that the upper bound here is nearly 4,000 Hertz. Now this rather insultingly says that 8-bit machines it's recommended the speed doesn't exceed 500 Hertz. That's a good 8-bit machine. Honestly, the ST, you don't want to get above 400. That's the problem that you see if you whiz a ball mouse far too far across the screen, or you spin its rollers and you just get jump, 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 jump. That's exceeding that 400 limit. So we define that as 400, and that is pretty much required for the ST. Buffer limit, this is how many additional quadrature inputs will occur after you stop moving. Now with a 400 rate limit and a 100 buffer limit, there's about a quarter of a second the mouse will continue to move if it hasn't caught up with your input movements. I find that about acceptable. Some people may want a lower number than that. I doubt it wants to go higher. But the key one here, and the difference between the Smalliermouse 2, and the Smalliermouse, and something like the Tom 2 is the DPI divider. So for every inch the laser mouse here moves, a certain number of quadrature inputs will be generated. Do we want that to be divided down so that we have to move further across the desk to move the same amount on the screen? And almost always the answer is yes. So I've put here that 2 or 3 are reasonable values. 2 works for this particular mouse. If you have a higher resolution mouse, you may want a higher divisor. The default here is 3. So these 3 items are the things that you may wish to tweak, although I would strongly advise against the top one. The bottom 2 are much more likely to be useful to you, and the DPI divider by far the most useful. So with that said, you shouldn't have to worry about anything else. You can just hit mouse. You can just hit up here on the green build button. Compiler warnings go up. We see that we're using a tiny percentage of what this chip is capable of. This is the smallest chip that can do USB hosting, which is why we use it. But it's capable of much more. One succeeded, all up to date. So we've successfully built our firmware. If we go up now to the programming interface, which is available as an icon up here, device programming, or is also in tools, device programming, you'll see that it's picked up our Atmel Mega DFU. If it hasn't, select it from the menu. The device should be pre-configured because this project is for the 8090 USB 1287. But we can apply it. Once we've applied, we see that some tool information pops up. The device signature here is missing, so we can read it. And once we've got a signature there, reading device OK, we know that it is connected and talking to the chip. Click on Memories. And here is where we do the programming. All of these things should be preset for you. There's an option here to erase before programming. I found that slightly unreliable. I would recommend to just erase and program as separate steps. So first of all, we press erase, erasing device, OK. Now, I've found sometimes you can press program and it works, sometimes you can't. The most reliable way is if you click read again up here to get the device signature back. If it comes back with reading device OK, we are now safe to press program. Program OK, verifying OK. Now, personally, as I mentioned, I prefer the divide by 2. So if we change that to 2, save, build, 1 succeeded, back to the programming center, apply, read, memories, erase now, erasing OK, read, program, programming OK, and let's go and look at our results. So back to our STE, here we are in high-res mode. We'll connect our mouse to the USB side and we'll plug in to the STE. To be honest, I recommend doing that when it's powered off, but just so that I had the screen up straight away, I've plugged in direct. You can see the mouse is powered up and there we go, it's working. This is in the divide by 2 setting. So you can see I can move quite well, cover most of the screen. Nice smooth motions, good accuracy. Perfect. I will just show you the divide by 3 mode so you can see the difference. I've just reprogrammed it as shown before into divide by 3 mode. Now when we connect it up, you'll see the response is a lot more muted. I have to move a lot further to cover the screen. My circles are a lot smaller, it's a lot tighter. It's much more like using an original Atari mouse, to be honest. Not that that is a good thing. Accuracy is obviously still just as good. If anything, more so, because obviously it's dividing all my movements by 3 instead of by 2. That's the purpose. Now, if you had a really, really high DPI mouse, you could divide that by further, you could divide that by 4. There's no real upper bound on how far you can divide it, other than the quadrature limit is 400 impressions per second, and you don't want to get to the point where that's never approached. So there we have the Smalliermouse 2, and more specifically the Smalliermouse variant with the Smalliermouse variant firmware. So I'm very happy with that. So I shall remove my reset line, clean that up with a little bit of braid. And we have a finished product. Now if we combine that with a wireless mouse and a wireless dongle, that is perfectly proportioned to fit under the keyboard bay of your SD or your Falcon. Thank you very much for watching. I hope you've liked that, and I hope it's made you want to build one. See you next time.